Our next presentation is entitled Image Analysis and Regression Modeling for Peanut Symptoms and Identification, and our speaker is Hope Becton.
Good morning. Can you hear me?
Yes, we can.
Okay. Thank you for that introduction. Okay, here we go. So in peanut production, disease is one of the most yield limiting factors, and there's an estimated 72% yield loss associated with the fungal diseases, and that's without the use of fungicides. Regardless, so the first step in any disease management program it should be an accurate diagnosis, regardless if it's caused by a fungus or not. However, the challenge is that some may not have proper training, and it could be hard for them to differentiate between similar symptoms on peanut leaves. For example, on this slide, I have two images with peanut symptoms or peanut foliar lesions. However, one is caused by chemical injury and the other is caused by a fungal pathogen, Nothopacillora personata, which is the causal agent of late leaf spot. So the issues around improper diagnosis can lead to economic losses through purchasing of unnecessary pesticides, wasted time and labor, and even yield losses due to attempting to fix the wrong problem. And then there's also the environmental impact of non-target fungicide sprays that could potentially lead to fungicide resistance in that field. So one possible solution is to develop and provide a tool for fast diagnosis of foliar peanut symptoms to aid growers in their decision making. So our objective of this study is to use image analysis and regression modeling to provide peanut growers with a tool that is fast, easy to use, and accurate for diagnosing those foliar diseases and disorders. And our hypothesis is that image analysis and regression modeling can be used to predict or diagnose peanut foliar symptoms with greater than or equal to 80% accuracy. So moving on to the methods used. So the first step in our image analysis process was to collect and sort images based on their foliar symptoms. And we used a collection of Canopy and cropped leaflet images. So on this slide, there are some examples of the type of images that were included in this database. And we did make a point to include images that have, shadows or contain different symptoms, are, at a weird angle or maybe a little bit blurry, just anticipating those types of images being uploaded in the end use. So the next step is we entered, I entered data for each image into a spreadsheet. I manually went through each image and recorded, image name and the location, but I also performed a binary rating based on the presence of symptoms where 0 equals absent and 1 equals present. So for example, if the image I was looking at, if the image I was looking at had was symptomatic for hopper burn, I would place a 1 in the hopper burn column and 0s in the other columns. So the next step is we developed the Hope Color Index, or HCI, and so that process was taking asymptomatic and symptomatic leaflets in order to find colors that were specific to peanut leaves. And so this image on the screen is, or it's a canopy image with some light leaf spot. And so I just took a dropper and selected the center of one of those lesions, and it came out as this dark brown, and it gives you the RGB values. So what I did is I went through and recorded RGB values for, you know, those browns and the yellow halos and the greens and et cetera for different types of symptoms. And so we analyzed those RGB values using a k-means cluster and categorized those into 13 specific color groups. And then those colors were added to our analysis software, which we use batch load image processor, which was developed by Clemson. So now that we're ready to analyze those images using BLIP, I would, you know, pull up the software and I would select to upload my folder with all of the images. And so it would just, it would analyze everything within that folder. And the output is a CSV file with 544 columns of data. And so that data, the data are color space values, such as RGB, hue, saturation, chroma, and the HCI, which I just defined. And those were averages as well as bins. And so what the bins are basically just breakdowns of those colors into more specific ranges. So for our regression modeling, we used a breakdown of training 80% of the data set and testing on 20%. In the preliminary stages, we did look at a few different types of regression, but we decided on logistic regression, which is used to predict probability of binary dependent variables. And then we also ran stepwise regression just to narrow down the number of variables per model. As I already mentioned, there were 544 possible. And so our current models are healthy, hopper burn, late leaf spot, and tomato spotted wilt. Moving into results. So here we have the model for healthy. And so each of these result slides is set up the same. There's going to be a reference photo right here in the top right corner. There were 2,415 images used in the database used to train these models. And again, 80% training is on 100 images, and validation was 483 images. So here we have our ROC curve, or the receiver operating characteristic curve. And essentially what that is just a diagnostic tool. So on the y-axis, this is the sensitivity, which is also like the true positives. And then the x-axis is 1 minus specificity, or 1 minus the false positives. And so, you know, if this model was just completely worthless, the area under the curve would be 0.5, and the curve would follow the diagonal line in the middle of this graph. And if it was perfect, the area under the curve would be a 1, and it would basically make a triangle. So for our healthy training data set, the area under the curve is 0.8358, which means that there's this model has approximately an 84% chance of correctly categorizing or differentiating between a 0 and a 1. And so that's for the training data set. And then for our validation, the area under the curve is 0.8020. And so the accuracy of the overall model among training and the validation data sets was 82%. So it correctly diagnose 82% of this data set. So next we have the Hopper burn model. The area under the curve for the training data set is 0.9071, so it's a little bit better than the healthy. For the validation data set, the area under the curve is 0.8939 and an overall accuracy of 92% for the model. Next, we have late leaf spot, and the area under the curve for the training data set is 0.9283. And for the validation, the area under the curve is 0.8989 with an overall accuracy of 84%. And finally, we have the tomato spotted wilt model with the training data set area under the curve being 0.9476. And for our validation, the area under the curve is 0.9239 and an accuracy of 89%. So obviously this isn't a finished project. However, we were able to use image analysis and logistic regression to develop 4 models with their validation AUCs ranging from 80 to 93%. And then those models were able to diagnose the peanut foliar symptoms with accuracies ranging from 82 to 92%. So moving forward, we do plan to develop models for additional foliar symptoms of peanut diseases and disorders. And once those are finished, we will develop a user-friendly website or app where growers can upload their own images of peanut symptoms that they're finding in their fields. So at this time, I'd like to thank my graduate committee, especially my advisor, Dr. Dan Anko, and then Dr. Kendall Kirk for their guidance as far into this project. And I'd also like to thank everyone who has contributed to our collection of images. And probably most importantly, USDA for funding. At this time, are there any questions?
Thank you for that presentation. We have a couple questions. This is, Hope, this is probably the first time I've ever seen this where the first question comes from your major advisor. So we'll have to, this is from Dr. Dan Anko. And his question is, identification of a symptom from an image can help inform management options, but what other information is needed before an appropriate recommendation would be warranted?
I'm sorry, can you repeat that one more time?
Certainly. Dr. Anko's question is this: identification of a symptom from an image, as you've done, can help inform management options, but what other information is needed before an appropriate recommendation would be warranted?
Okay, so the question is, so we can identify image or symptoms from an image, but what other information is needed before a recommendation is made?
Yes, that's be my interpretation.
So I would say, I mean, there's a few things that would probably be necessary to ask, such as history of the field, you know, which cultivars have been, or varieties are used, their fungicide, or, you know, what management systems or programs are already in place in that field. So yeah.
Okay. All right. Thank you. The next question is from Dr. Cristiane Pilon. And her question is, have you considered to use thermal imagery? Do you think it would help in building your models?
Thermal imagery. We haven't discussed anything like that yet. We have discussed maybe adding in some like like the drone image, not thermal, but just like larger images of fields. But at this time, that's those aren't like our first priority.
Okay, thank you. Your next question comes from Dr. Albert Culbreth. His question reads, did the late leaf spot samples that you looked at vary in presence or absence of a halo? And if so, was this taken into consideration for the model?
Okay. So the question was if the late leaf spot images had halos, and was that taken into consideration for the model?
Yes. Whether or not they had halos or not, was that a consideration?
Kind of, but not. So the yellow halos were considered when developing that Hope Color Index. And but since that data, like that was added to the analysis software, so depending on whether that halos or not, that data was in the output. And so yeah, based on the models, it will take look at those parameters to see if it's important in building that model.
Okay. That's the time we have for questions. Thank you very much for your presentation and for your participation today.
Thank you.